Sorry, Professor, just give me one moment. I have to fix the web camera.
Yeah, no problem at all. Now it's ready.
And in the top right corner of like your screen, there's like a little thing.
Yeah, I don't know. Sorry, Professor, I don't know what's wrong with the webcam. So, um, yeah, you won't be able to see the
Oh, it's fine if I can't see them, as long as they can see what I'm doing.
Yeah, they can still see you. I don't know what's wrong with the webcam, though. Sorry.
Okay, that's fine. I'll just get started then. All right. Hello, good morning, everybody. I hope you're having a good day. So as a reminder, our second chapter quiz is tomorrow. So you'll need to make sure that at some point tomorrow you log in, set aside 1 hour to complete the chapter 2 quiz. So there is a review tonight. It's from 5 to 6 p.m. The link is both in Moodle and in the last course email that I sent out. And so that will give you the packet that's under the chapter 2 heading on Moodle. I think there's like 12 practice problems. So you can check that out. I would recommend trying those problems before you go to the review so that you have a good sense of sort of what you understand and what you need help with. So today we're going to be moving into chapter 3. This will not be on tomorrow's chapter quiz. And so chapter 3, sort of the big picture is that chapter 2 is laying a lot of the conceptual foundation of what a derivative is, right? So we spent a lot of time talking about the derivative is the slope of the tangent line, which helps us approximate how much a function is changing at a point, right? So that's what we've been doing in a lot of different ways. And what we're going to be doing in chapter 3 is saying, okay, now that we understand what the derivative is and what a derivative function is, how do we formalize it to make our lives easier? So we're going to be doing a lot more sort of formulas and calculations, the conceptual work, but with that, there's going to be sort of an upswing in algebra. So if algebra is something that is complicated for you, make sure that you get help early and often at drop-in help for any of the algebraic steps that might be tripping you up. You don't want to wait to get help on that kind of stuff. So I'm going to go ahead and switch to StockCam. Okay. And as we start thinking about this, you know, we are going to be coming up with some algebraic formulas to help us understand derivative patterns. And sort of the underlying thing that produces these formulas for us comes from the definition of derivative. So we're not going to do a whole lot of work with the definition, but it is important to know that it's the definition that allows us to generate our formulas. So the definition of derivative looks like this. I think you saw it once back in 2.2, but we haven't really done a lot of work with it. But the idea is that the derivative formula is the limit as h goes to 0 of f of x plus h minus f of x over h. And what this is doing is it's taking secant lines and getting them closer and closer until it becomes a tangent line, which we talked about earlier in chapter 2. So the way that we sort of apply this formula when we want to find a derivative of anything, there's some examples here. So I'm just going to jump to the second example because it's a little more complicated. You can look through the first example to see it on your own here. But this is our definition. The limit is h goes to 0 of f of x plus h minus f of x plus h. And we want to use to find the derivative of a linear function that has a b of 0, so mx. So m is some number and x is our variable. So when we do f of x plus h, that's like our composite function. So we plug in x plus h wherever we see an x. So we get m times x plus h minus f of x, so minus mx divided by h. We want to simplify and group like terms. So we distribute the m, we get something that looks like mx plus mh, and we still have minus mx. So the mx's cancel, and we're left with mh over h. The h's are going to cancel, and once we have the h out of the denominator, we can let h go to 0 because there's no h left, and we just get m. So what does that mean, right? So I'm going to draw a quick picture. So if we have a function that say, let's say this is 6x. Okay, so again, mx is a linear function that goes through 0. What this is saying is that if your function is 6x, then the derivative of that function is 6, right? It's just the m. And now this should make sense because we know that if we were to draw in the tangent lines, right, of a linear function, we know that the slope of a linear function is the rate of change, right? It lies on the line. So the slope of all those tangent lines is 6. So what that tells us is whenever we have a term that's a number times the variable, so a linear function, right, that the derivative is just going to be the slope of that line. Okay, so what ends up happening is if you take this formula and you apply it to all sorts of different functions, you start to notice patterns of what the derivative looks like. And then what we can do is take those patterns and turn them into formulas so that we don't have to do the arduous work of the algebra involved of using this limit. So this particular one is not very complicated, but if we were to do something like x to the 10th, this becomes really, really complicated, right? Because we have x plus h to the 10th. So to simplify that is really, really difficult and time consuming. So if we apply this to a bunch of different polynomial terms, so things like x squared, x cubed, what we find is that there's a pattern. And the pattern is that if you have x raised to some power p, and you apply this whole process, that the derivative always ends up being px to the p minus 1. So what does that mean? That means the power has come down in front, and we subtract 1 from the power. So an example, let's say we have x 100th. Okay, What this formula is saying is that the derivative function for this, so it would graph the derivative at every point if we were to graph it, the 100 is going to come down in front, and then we're going to subtract 1 from the power. So 100 minus 1 is 99. So when we work today, we're going to be considering functions that are polynomial terms, and then we'll also consider sine and cosine later. The next class we'll look at exponentials and logarithms, and we'll just kind of keep building our formulas up. So the formulas that we're going to start with, there's 3 of them as identified on this page. So the first one, if you have a function that's just a constant, so f of x equals 10, f of x equals 20, the derivative is going to be 0, okay? If you have a function that is linear, a linear term, the derivative is just the slope of that line. If you have a function, x raised to some power p, the formula we use is px to the p minus 1. So these are the 3 formulas we're going to start with, okay? And so here you can see a summary of these particular formulas. And what we're going to be doing today is we're going to get really, really comfortable using and applying these formulas and figuring out when to use them, when not to use them. And then we're going to add on some other rules and sort of discuss, well, can we still use these formulas in this case and in that case? And we're going to kind of build from there. So these are the 3 formulas. And as we go, we're going to be adding to this table our list of rules. And it's a good idea to keep it handy. I'm going to grab something to lift this up a little bit, which I think will help the size a little bit. Here we go. Okay. So for example 1, we're going to try to apply these 3 formulas to these particular functions. So we have 7 x, x squared, x to the 5th, x to the negative 4, x to the 2/3, and x to the negative 4/5. So we're going to look at these formulas, think about which one is going to apply. So is it a constant? Is it a linear term? Or is it x raised to some power p? Then we're going to apply the formula to find the derivative. Now, I want to just remind you that if you subtract 1 from a negative number, it becomes more negative. And if you subtract 1 from a fraction, you have to find a common denominator to think about what it means when you subtract 1. So I want you to try these. So there's A through G. See if you can figure out what the derivative is going to be based on these 3 rules. I'm going to give you about 2 minutes, and then we will go through it together. Okay, take about 30 more seconds. All right. So let's start with A. So here I have f of x equals 7. So what I want you to notice about the 7 is that it's not attached to anything. Okay, so that means that we are using this first rule, that we have a constant. The only time we have a constant is if it's not attached to a function, right? So it's got to be completely by itself, just like it is here. And so the rule says that when you take the derivative of a constant, you're going to get 0. Okay, so think about what f of x equals 7 looks like, right? Looks like this. Y equals f of x equals 7, right? If you have a constant, it's just a horizontal line. So it's this line here. So if you were to take the derivative and draw on the slopes, they would all be horizontal. So at every point, the derivative is 0. So that's why the derivative of a constant is 0. Now, the next term, we see the 10 and we think, okay, 10 is a constant, but that 10 is attached to an x, which means we're not going to use that first formula because that's when constants are by themselves. Instead, we're now looking at the second formula because here we just have a constant times x. So according to that formula, if you have a constant times a single x, the x has no power, well, it has a power of 1, but we'll write it. The derivative is going to be just the slope, which is the number attached to the x. So for the second one, our derivative is just going to be 10 because that is the derivative of 10x. Now for C, I don't have any constants in front, but I have an x squared, so x to the power of 2. So this is a case where I have an x raised to a power. So when I have x raised to a power, my formula is that that power will come down out front. So the 2 comes down in front, and I subtract 1 from the power. So I have 2x to the 1 power. We don't usually write the 1 power, so I would write this as 2x. Okay. Now the next one, I see I have x to the 5th. So x to the 5th is again x raised to a power. So when I take the derivative of x to the 5th, the 5 comes down and I subtract 1 from the 4th. I get 5x to the 4th. Okay. Now the next couple are tricky just because of the algebra involved in applying the formula. Okay. So here, for the next one, I have x to the negative 4. When I take the derivative of x to the negative 4, the entire power comes down out front. So negative 4x. And now I subtract 1 from the power. So negative 4 minus 1 is going to give me negative 5, right? So again, if you subtract 1 from a negative number, it becomes more negative. For F, I have x to the 2/3. So when I take the derivative, again, the entire power comes down in front. So 2/3 x. And now I have to subtract 1 from the power. So again, I'm going to be really careful. 2/3 minus 1. We'll just kind of do a quick reminder over here. You need a common denominator for the 1. Let's write that as 3/3. So 2/3 minus 3/3. So that's going to give us negative 1/3. So my new power is negative 1/3. So I have 2/3 x to the negative 1/3. And then finally, last but not least, we have x to the negative 4/5. So the negative 4/5 comes down. And when we subtract 1 from the power, right, again, we have negative 4/5 minus 1. We can write the 1 as 5/5, but because this is negative, this becomes negative 9/5. Okay, so we do a lot of fractions in this work. So if this is stuff that you don't remember from algebra, you want to make sure you practice this and be really careful with your powers. Okay, so these are really good examples of the types of functions you're going to see when we apply these 3 types of formulas. Okay, so the next thing we want to bring in is what if our function has a constant multiplied in front. And for the first two formulas, that doesn't really change anything, right? Because if you have a constant times a constant, you still just have a constant. So that doesn't change anything. And if you have a constant times x, we already know what to do. But the real question is, what if we have something in front of our x to the p, right? What if we have 4x squared or 12x squared, something like that? So if you take the derivative of a constant times a function, you can actually pull the constant out front and multiply it by the derivative of the function, which means you have the constant times the derivative of the function. So what does that mean, right? That means that if you have something like f of x equals, I don't know, 3x squared, okay? That 3 is going to multiply the derivative of x squared. So we have 3, and then we take the derivative of x squared, apply a power rule, and that is 2x. So the derivative, 3 times 2x, is just 6x, okay? The way we often do this in practice is we say, when the 2 comes down, it multiplies the 3, giving us 6x, and then we subtract 1 from the power, okay? But what's happening sort of behind the scenes is that this constant is being carried along and multiplies the derivative of the functional part, okay? So let's do some practice problems that have some constants here. So the functions, we have pi, we have 4x cubed, 9x to the 20th, negative 3x to the 5th, 6x to the negative 6. So again, be careful with negative powers. 6x to the 1/3, being careful with powers that are fractions, and 7x to the negative 2. Okay, so I want you to take 2 minutes, see if you can figure out what the derivatives of these are going to be by using these rules, but now we have a constant in front. So the constant will multiply the derivative of the function. Okay, try that out, and then in 2 minutes, we'll go through it together. Okay, take about 30 more seconds. Okay. So when we start looking at these and we look at the first one, we have to be a little bit careful. So this is a pi. And when we talk about pi is just a number, right? It's an irrational number that goes on forever. It's approximately 3.14. But what you notice here is that there's no x. X is our variable and there's no x, which means that this is just a constant by itself. So that defaults us back to the first formula. And so we say that the derivative of that is just going to be 0. Okay, and again, that's from our first formula because the pi is by itself. Okay, now for our next function, we have 4x cubed. So when we take the derivative, we're applying this constant multiple formula. It says that the 4 is going to multiply the derivative of x cubed. So here the 3 is going to come down to multiply the 4. That'll give you 12x, and then we subtract 1 from the power. So 3 minus 1 is going to be 2. So that's how we do that in practice. But again, behind the scenes, what is happening is that we are getting 4 times the derivative of x cubed, which is going to be 3x squared. The 3 comes down, we subtract 1 from the power, and then we multiply the 4 and the 3 together, and that's where we get the 12. Okay, so again, in practice, we do it all in one step. So what's happening behind the scenes is this constant multiple rule. So let's look at the next one. So we have 9x to the 20th. So again, we want to be careful with our algebra here. So the 20 comes down to multiply the 9. So 9 times 20 is 180. And feel free to use your calculator if you need to on some of the bigger numbers. And then we're going to subtract 1 from the power. So it was 20. So now it's 19. So 180x to the 19. Our next one here, D, we have negative 3x to the 5th. So when the 5 comes down, it multiplies the negative 3, and we get negative 15x to the 4th. Okay, so since there was a negative with our constant, when 5 comes down, it multiplies negative 3. For the next one here, we have 6x to the negative 6. So the negative 6 comes down, the whole entire thing, the negative and the 6, to multiply positive 6. So we get negative 36x. And now we have negative 6 minus 1, which is negative 7. Okay. So again, we're being extra careful with our powers that happen to be negative. So for the next one, we have 6x to the 1/3. So here we have to be careful with our fractions. So the 1/3 is going to come down and multiply the 6. So 6 times 1/3 is 2. And again, if you want to double check that on a calculator, that's totally fine. Then we have an x. And now we have 1/3 minus 1. So 1/3 minus 1 is negative 2/3. So we end up with 2x to the negative 2/3. And then finally, we have 7x to the negative 2/5. So when we take the derivative of that, the negative 2/5 comes down in front. So 7 times negative 2/5, we get negative 14/5 x. And now negative 2/5 minus 1 is going to give us negative 7/5. Okay. So as I mentioned, there's a lot of that goes into these formulas. Now, one of the things I really want to highlight now that we've done, a couple of these and applied them is what we are getting. The original function and the derivative function. So if we want to talk about the instantaneous rate of change, we would need to plug in the value that we were looking for, right? So the instantaneous rate of change of 1 is different than the instantaneous rate of change of 5. So if we wanted to know the instantaneous rate of change of 5 for one of these functions, we have to plug a 5 into the derivative to get that rate of change, right? But the value of having the function is that we can plug in any value we want. Okay, so the next problem is sort of more closely where you're going to see a lot of the functions. And this particular problem is just meant to help you remember some of the algebraic sort of rules that we use with functions. So we're just going to see what you remember. But if you don't, that's fine. But here's what's happening. So we have the square root of x. We have 4 over x cubed. And we have the root of x squared. And what we want to do is we want to use our formulas, particularly this last one, x to the p, to solve these derivatives. Now, in order to do that, that means that we have to rewrite all 3 of these into an algebraic form that looks like x to the p before we can use the formula. So this particular problem is meant to help you remember how to rewrite functions. One point to make for the second one is that you cannot use the derivative of x cubed in the denominator. You have to figure out how to get it out of the denominator. So I'm going to give you 2 minutes to remember, try some things out even if they're not right, and then we'll review the rules for rewriting so that we can take the derivative. Okay, so try it out, and then we'll go through it together in 2 minutes. Okay, take about 30 more seconds. Okay, so let's think about what the algebraic properties are that we need to use here to be able to solve these. So that means that there is a step before we can take the derivative, which is rewriting the function. So here, for the first one, if you have the square root of x, the way that we rewrite this algebraically is x to the 1/2 power. So when we then take the derivative after we've rewritten, we can now use the power rule because we've turned the symbol into a power, which is a number. So now when we apply the rule, the 1/2 comes down and we subtract 1 from the power. So 1/2 x to the -1/2. Now, I will mention that just like we will start seeing things more in this form, we will also see answers simplified back into things like roots. So we'll talk about simplification after we do all 3 rules, just to sort of highlight what that might look like. So for part, again, we need to rewrite. So we have 4 over x cubed. So the rule that we're using here is that we can bring a term up from the denominator if we make that power negative. So we can rewrite this as 4x to the negative 3. So now when we take the derivative, we have something that's in the form of the power rule, where we have a constant multiple and we have x raised to the power. So here the 3 or the negative 3 is going to multiply the 4. We get negative 12x. And again, we subtract 1 from the power, so it becomes more negative. We get to the negative 4. Now for the last one, we're applying the 5th root of x squared. And so there's sort of 2 steps in simplifying this, and you can do this all in one step if you're comfortable, but the 5th root is going to be the 1/5 power. Square root is 1/2 power. The 3rd root would be the 1/3 power. And when you have a power raised to a power, you multiply those powers together. So this becomes x to the 2/5. Okay, so again, this step was all just rewriting the same function. This is the same exact thing as this. Okay, we haven't done any derivatives yet. We don't do the derivative until we apply the power rule. So now that we have it in the right form, we can apply the power rule. So the 2/5 comes down, we subtract 1 from the power. So negative 3/5. Okay, so you see that we were able to apply the rule directly, but what does it look like when we simplify it, right? So for all 3 of these, you see that they have negative powers, which means that they're going to go back down into the denominator. So I'm actually going to do the middle one first. I think this one will be the most straightforward to start with. So we have negative 12x to the negative 4. We don't want to have a negative in our final answer. So we're going to have negative 12 over x to the 4th, because we can bring this term back down by changing the sign of the power. Okay, so that's how you might see that simplified. Now for the first one, there's sort of 2 steps of simplification. So we're going to use that same idea that we want the power to be positive. So this becomes 1 over 2x to the positive 1/2. So notice that I already had 1 over 2. So this goes into the denominator when I change the power. But the 1/2 power is again the square root. So we could also write this 1 over 2 times the square root of x. Okay, so these 3 things all represent the same derivative function. Now, one caveat here is if you are doing homework, you don't need to simplify, right? You can enter answers like this, and Wiley should accept it. The reason you need to understand what it looks like is because if you take a quiz and we have simplified it to this, and you have done the work to get here, you need to know from algebra that these are the same thing, right? So if you see this, that you know it's the right answer. So that's why we're sort of looking at these this way. Now let's look at the last one. We have 2/5 x to the negative 3/5, right? So again, we're going to start by make this power positive. So we have 2/5. Now we're going to bring this down to the bottom. So we have x to the positive 3/5. And now, similarly to what we had here, we want to put the 5th root back in. So we have 2 over 5. So that's just the 2/5. That doesn't change. But now we're going to have the 5th root. So we pulled in that 5 and made it a root. So what's left is x cubed. So that's how we could simplify this particular derivative. And again, if you are just calculating a derivative for the sake of calculating it for homework or for practice, you can leave it like this, but you do need to be able to recognize other forms of simplification for quizzes and things, because in the mathematics community, we do tend to simplify to make things easier for the reader and things like that. And it's important, and I'm sure you did a lot of this back whenever you took algebra, to be able to see multiple representations of the same thing. So these are sort of the three algebraic rules that we pull in pretty quickly into derivatives. So now that we've reviewed them, hopefully you're going to remember and can apply them moving forward. Okay, let's look at the next rule here. So sums and differences. So far, all of these things we've looked at have been single terms, right? So just one term that we were dealing with and finding the derivative. So the question comes up, what happens if we try to take the derivative of two functions that are either added or subtracted? So if you have f of x plus g of x, right? X squared plus x to the fourth. Well, fortunately, we can take the derivative of each term separately and add the results together, okay? So if you have f of x plus g of x, and you want to take the derivative of that entire function, it's just f prime of x plus g prime of x. And the same thing is true if you are subtracting the function. So if you are adding or subtracting terms, you can just take the derivative of each term. You cannot do that with multiplication and division. We're going to learn special rules for how to deal with those in probably 2 or 3 classes from now. But for addition and subtraction, we can just go term by term. So we're going to go ahead and practice this with these. So again, we're going to just apply the power rule to each term, or one of the other rules we have of the 3. You'll see that there's some roots in here to practice our writing and rewriting and algebra skills. So we're going to try these 4. I'm just going to read them to you in case the numbers are small. The first one is x to the 5th minus 2x squared plus 6x plus 1. The second one is 3x cubed minus x to the 1/3 plus the square root of x. The third one is 10x to the 4th minus the 4th root of x plus 2 over x cubed. Then the last one is negative 3x to the negative 3/4 plus 2 times the square root of x. Okay, so again, what we're learning is that we can take the derivative of each term separately and put them back together to get the derivative of the function. So it's just more practice with our rules. So I'd like you to take 2 to 3 minutes, try to find the derivative for each of these 4 functions using all of the rules and algebra we've been talking about, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so as we evaluate these, we're going to be going term by term. So we start with the x to the 5th term, and when we take the derivative, we use the power rule. So the 5 comes down and we subtract 1 from the power. So we have 5x to the 4th. Then we have minus, now we have 2x squared. So the 2 comes down to multiply the 2, giving me 4x to the 1 power. And again, we don't usually write the 1 power, so I'm going to leave that off. Our next term is 6. So this is a different rule. This is our linear term. And we know that when you take the derivative of a linear term, you just get the slope. So here we're left with a +6. And then the last number, +1. That 1 is all by itself. And so the derivative of a constant is just 0. So I am going to write +0 just to remind us that we had a constant there, but we don't have to write a +0. We'll stop doing that after today, but just so to remind us that we use that rule. Now, for the second one, I noticed that the last term has a square root. And so what I'm going to do is I'm going to remind you that the square root of x is the same thing as x to the 1/2. So as we take our derivative of that term, we know how to apply the power rule. So here for this second term, again, we're going to go term by term. So we have 3x cubed. So the 3 comes down to multiply the 3 in front. That's going to give me 9x, and I subtract 1 from the power. So I have 9x squared minus, now the second term is x to the 1/3. So the 1/3 comes down, and we subtract 1 from the power. So we get -2/3. And then finally, the last term was the square root of x. But in order to use my rule, I need to rewrite it as x to the 1/2. So that means the derivative is 1/2 x to the -1/2. Okay, we're not going to simplify these just because we don't have a lot of space. But again, the simplification rules that we talked about before could be applied here. Now, looking at part C, I noticed that there's 2 different terms that need to be rewritten. So I'm going to make a little bit of a note. So the middle term is the 4th root of x. So the 4th root of x, as a reminder, is x to the 1/4. And then 2 over x cubed, as a reminder, is the same thing as 2x to the -3. We can bring that term up by making the power negative. Okay, so let's take a look at what our derivative might look like here. So our first term, we have 10x to the 4th. The 4 comes down to multiply the 10. That gives me 40x cubed, because I subtract 1 from the power, minus, now I have the 4th root of x. So I remember that that's the same thing as x to the 1/4. So when I take the derivative, I get 1/4 x, and now I subtract 1 from the power, right? So 1/4 minus 1 will give me -3/4. And then for the last term, I notice that I'm going to have plus 2x to the -3rd, and I need to take the derivative of that. And I'm not going to write the plus yet, because what I noticed that since this power is negative, when I take the derivative, that's going to give me a negative term, and so I will write it as a minus instead. So when I take the derivative of this last term, the -3 comes down to multiply the 2, giving me -6x. And then I subtract 1 from the power. So to the -4. You can write it as plus -6. That's the same exact thing. That's just a matter of preference. Okay. And then for our last term here, I notice that I have another square root of x, but I've already recognized that that's the same thing as the 1/2 power. So I'll just keep that in mind when I'm taking this last derivative. So my first term here, I have -3x to the -3/4. So I have to be really careful whenever I have fractions and negatives. So the -3/4 comes down in front. The negatives are going to cancel. And I'm going to be left with 9/4 x. And now I'm going to subtract 1 from the power. So -3/4 minus 1 is going to give me -7/4. Okay, plus now I have 2 square roots of x, but again, I know that's the same thing as 2x to the 1/2 power. So when I take the derivative, the half comes down to multiply the 2, giving me a 1. I have 1x, and now I subtract 1 from the power. So that gives me -1/2 power. Okay. So again, we're trying to be really comfortable with these formulas, and we're trying to be really careful about the algebra that comes up with them. Okay. So the next thing that we're going to talk about, right, still thinking about these 3 formulas we have, is the second derivative. Last class, we highlighted why the second derivative is important. So being able to find a formula for the second derivative will be really helpful. So as a reminder, we use the notation like this or like this, right? This is what helps us understand what the second derivative notation looks like. And so to find the second derivative, we're going to take the first derivative which is what we've been doing. And then we're going to apply the same rules to the first derivative function that we have found. Okay, so what does that mean? So let's say we started with the term f of x equals x to the 10th, right? What we know so far is that for the first derivative, the power comes down and we subtract 1 from the power, 10x to the 9. To get to the second derivative, we look at the first derivative and see what rule we need to use, and we apply it again. So again, we use the power rule, and now the 9 comes down to multiply the 10. We get 90x, and we subtract 1 from the power to the 8th. So we apply the rule again, or whichever rule is appropriate, to then get the second derivative. Okay, so we're just using the rules more than once now. Okay, so here we're going to try this. We're going to compute a first and second derivative for these 3 functions. And they're a little bit, they're meant to really make you think about it a little bit. But for the first one, we have 6 minus 3 over x plus 3 over x squared plus x to the 1/3. You'll take the first derivative and then think about how you can apply and get the second derivative. The second function is x to the e. So think about what e is and how we might apply the formula and what that might look like. And then the last one, we have 6x to the 7th minus 20 square roots of x. So again, with square roots, think about how do we rewrite that? How do we then apply that? And then, taking the first and second derivative. So I'm going to give you about 3 minutes, 2.5 to 3 minutes. Hopefully you're able to get at least the first derivative for all these functions, but then just try to carefully apply the algebra and see if you can get the second derivative, and then we will go through it together. Okay, so take about 30 more seconds. I've written the first derivative for each of the functions here, so you can quickly eyeball it to make sure that that is looking like what you were getting. But take another 30 seconds to really think about your second derivative. Okay, so for our first function, we have a 3 over x and a 3 over x squared. So over here, I wrote how we would rewrite those. And so we have 3 over x is the same thing as 3x to the negative 1. 3 over x squared is 3x to the negative 2. So positive. We'll talk about that in a second. So the first term is a 6. And 6 is a constant that's by itself. So when we take the derivative, we get 0. So then we have minus 3x to the negative 1, right? So this minus is in front of this term. So when you take the derivative, the negative 1 comes down in front and makes that positive 3. And then we subtract 1 from the power. So we end up with 3x to the negative 2. Then we had plus 3x to the negative 2 when we rewrite it. So when the negative 2 comes down to multiply the 3, we get negative 6x to the negative 3. And then finally, the last term, we had x to the 1/3. So we get 1/3 x to the negative 2/3. So now when we take the second derivative, the 0 goes away. So we can just start with the terms that are non-zero. We have 3x to the negative 2. That becomes negative 6x to the negative 3. So the negative 2 came down. We subtract 1 from the power. The next term, negative 3, comes down to multiply the minus 6. So we end up with plus 18x to the negative 4th, because we're subtracting 1 from the power. And then here, the negative 2/3 comes down. So we end up with minus 2/9 x to the negative 5/3. So again, we're using the same rules here to go to the next derivative. And the reason why second derivatives are sometimes more complicated is just because the first derivative, you tend to get more of fractions and negative numbers. So when we have x to the e is a number. So the power rule says that that number comes down out front and we subtract 1 from the power. So this is a common way we would write this because e is irrational. So you can't subtract 1 from it and make a nice whole number. So we would write this as ex to the e minus 1. And so if we were going to take a second derivative here, the e minus 1 term is going to come down. So we have e times e minus 1 x. And if we subtract another 1 from the power, we have e minus 2. So this one's a little goofy and a little strange. You could certainly sub out pi for e and you would get something similar. But just keep that in mind when you have these sort of non-traditional numbers in your problems. Okay. For the last one, we had 6x to the 7th is our first term. So the 7 comes down to multiply the 6. We get 42x to the 6th because we subtracted 1 from the power. Remember that the square root of x is x to the 1/2. So when we take the derivative, the half comes down to multiply the 20. So we get minus 10x, and then we subtract 1 from the power, to give us negative 1/2. So now when we go ahead and take the second derivative, the 6 is going to come down and multiply the 42. So we're going to get 252x. We subtract 1 from the power, so to the 5th. And then the second term, the negative half comes down and multiplies the minus 10. So we get plus 5x, and we subtract 1 from the power. So to the negative 3/2. So I want you to be extra careful when you're thinking about how complicated you think this process is, because there's a difference between not understanding the rules of the derivative and messing up the algebra when you're doing things like subtracting one from the power or things like that. So separating out if you're struggling with algebra versus the derivative rules can be helpful when we're trying to help you sort of do your best. I'm going to skip ahead a little bit because there's 2 examples I want to make sure that we do that you have for homework. So we're going to skip to example 8 because I think this will be new. Example 6 and 7, if you want to see them done out, are on the asynchronous videos. So example 8 we're going to do is find the equation of the tangent line. So we've spent a lot of time in this class talking about how the derivative is the slope of the tangent line. And now that we have formulas, we can go ahead and extend it to actually finding the full equation of the tangent line. So we know that lines have equations that are y equals mx plus b. So how do we go ahead and find the equation of the tangent line to this particular function at x equals 3? So in order to get the equation of a line, you need either 2 points or a point and a slope. So what we know is that the derivative will give us the slope of the tangent line at any point. So what we're going to do is we're going to do the derivative of this function, which is going to be, let's see, 2x minus 4. Because the first term was x squared, the 2 came down, so 2x. The second term was a linear term, so we just get the slope, and the 1 goes away because it was a constant. So what this means is if I am to plug in 3, that will tell me the slope of the tangent line at 3. Okay, so 2 times 6 is 12, right? Oops, that should be a 3. I said plug in 3. 6. Plugging in 3, sorry about that. 2 times 3 is 6 minus 4 gives us 2. So this is the slope of the tangent line, right? And it's the slope of the tangent line that touches at 3. If I were to ask you what was happening at x equals 5, we would get a different value and a different tangent line, right? So it's really important that we're looking at what is given and where we are evaluating. So we have the slope. And so in order to get the equation of a line, we need a slope and the point. So the point on the tangent line is the point where our tangent line touches the function. So if we were to plug a 3 into the original function, we can get the point where it touches. Okay, so if we were to plug in 3, we get 3 squared minus 4 times 3. So 9 minus 12 plus 1, that's going to give us -2. So we have the point 3 comma -2. We know the slope of the line is 2. So we can start putting that together into y equals mx plus b. So my m is the slope. So now I'm really close to having the full equation of my line. To solve for b is why I need this particular point. So if I plug in this, right, 3 for x and -2 for y, that will allow me to solve for b, right? So here, 2 times 3 is 6. I subtract 6 from both sides, and I get b equals -8. So what that means is that the final equation of my line is y equals 2x minus 8. So this is a pretty common problem that's going to come in chapter 3 where we're finding the equation of a tangent line. So these are the things we need to remember. We need a slope and we need a point. The slope we get from taking the derivative and plugging in the point that we are evaluating. That's going to give us the slope of the tangent line by definition of the derivative. We also need a point on our line, which we get by plugging the evaluative number into the original function, because that is the point where the tangent line touches. So it's a shared point. Once we have the slope and the point, we put it together, we get y equals mx plus b, we are able to get the equation of the tangent line. Okay, so that's something that we'll be practicing a lot in chapter 3. Now, the last sort of thing I want to make sure that you know before you leave today is derivative of sine and cosine. So this gets added on in the section. It gets used throughout chapter 3. So these are related. So when you take the derivative of the sine function, if you use the limit formula that we saw earlier, and you look at all the different sort of points for the derivative function, it turns out that the derivative of sine is cosine, right? That's pretty convenient. And the derivative of cosine is going to be negative sine. Okay, so we have to be a little bit careful in remembering where that negative is. But other than that, it just becomes a new rule that we can apply when we're taking derivatives. So, for example, okay, 6 cosine x, the constant multiple rule works for us here. So the derivative will be 6 times the derivative of cosine. The derivative of cosine, we said negative sine. So I'm going to pull the negative to the front, as we normally do when we write final functions, and I get negative 6 sine x. For the next one, we have sine x plus 1. The derivative of sine is cosine, so we're applying our sums rule here. And then plus 1, the derivative of 1 is 0 because of the constant. So we just end up with cosine. And then last but not least, right, we have x cubed minus 2 sine x. So again, we can go term by term because they are separated by subtraction. The derivative of x cubed is 3x squared minus 2, right? So the 2 is going to multiply the derivative of sine. Derivative of sine is cosine, right? So bringing in the on sine and cosine is not going to sort of change things hugely from what we already know, but it does add to our list of rules of things that we can do, okay? So here, again, equation of the tangent line. So this is what I was saying, it's going to come up quite a bit. If we want to find the equation of a tangent line, we now have a cosine function. So how does that impact the process? Again, we would need the derivative to get the slope. Okay, the derivative of 3 cosine is negative 3 sine x. We want to evaluate this at pi over 2. Okay, so we're going to plug in a pi over 2. And this is a good time. If you don't remember your circle and the values, and you are going to be plugging these things into your calculator, make sure that your calculator is in radians. Okay, so sine of pi over 2 is 1, which means that our slope is negative 3 times 1, which is negative 3. To get our point, we would need to plug pi over 2 into the original function. 3 cosine of pi over 2. Okay, cosine of pi over 2 is going to be 0. So we have the point pi over 2, comma 0. So now we have a slope and we have a point. We're going to put it together in y equals mx plus b. So we start by substituting in our m, and then we use our point to solve for b. 0 equals negative 3 times pi over 2 plus b. We want to leave pi's as pi's. So don't turn this into a decimal because you will make it less accurate. So here we have negative pi over 2. So we add that over. So b is positive 3 pi over 2. That means that our final equation, when all is said and done, if y equals negative 3x plus 3 pi over 2. Okay, so this is an exact answer. Again, don't turn that into a decimal because that turns it into an approximation. But that should give you all the rules that you need to do your homework. Again, if you want to look at the example 6 that we skipped, it's on the lecture videos. And the same thing for example 11. That's just practicing plugging in values into derivatives and functions. Okay, so good luck on your chapter 2 quiz tomorrow, and I will see you guys all on Monday.